Hello, this is the walkthrough for the DC electricity paper. This is Unit 1 of the UFP physics course. This is a walkthrough, so I'm going to go through and take you through each question, show you how to answer them. So we start off with the paper itself. It's the usual stuff. It tells you all the instructions at the front. It's always a good idea to start by reading that. Notice you shouldn't be using any correcting fluid, and you can use a scientific calculator. There are 75 marks in total of the paper. You know that at the end of the paper there are always some multiple choice questions. So let's go through the paper itself. On the inside cover there are all those constants, which I strongly advise you to keep handy as they come in very useful, and also the ones you may find most useful would be the questions on capacitors and resistors, Kirchhoff's law, and of course capacitor discharge right at the bottom here. So let's start with question number 1. It's a simple circuits question. You've got a circuit diagram for a hairdryer. The motor is used to run a fan which is moved which moves air over a heating element. The element can be switched off while the fan is running, and the heating element cannot be switched off unless the fan is running. So we start off with the first part, which is state the current flowing through the heater when switch 1 is open. What that means is that when you're looking at that particular question, you know that you should be looking at for the command word. So your command word here is to state. State means it's a simple statement. So when switch S1 is open, obviously no current can flow throughout any of the circuit, so the answer is 0. S1 is now closed, but S2 remains open. Calculate the current flowing through the motor. So S2 is still open, S1 is closed. You've got the motor here, and it tells you the resistance of the motor is 92 ohms. So we're starting off with Ohm's law. V equals IR. I equals V over R, where V is 230 volts, R is 92. You can and therefore should always use your calculator. So here it is on the calculator. 230 divided by 230 divided by 92 gives you 2.5 amps. So the answer is 2.5. In an ideal world you'd do it twice, but I happen to know that it is 2.5 amps, so I'm going to put my answer in there in the space provided. Okay, now on to part 2. So we're calculating the power used by the motor and including the correct unit. So power, I'm going to use V squared over R. Okay, you can use IV because you've got the current. You could use P equals I squared R, I suppose, if you wanted to as well, but I'm going to use this one. So it's 230 squared over 92, which comes out to be 575 watts. So it's 575 watts is my answer. Okay, so that's question B part 2 done. On to the next question, which is S1 and S2 are now closed, and you have to calculate the current flowing through the heater, the current flowing out of the battery, and the total electrical power used by the hairdryer. So we know that we've got, if this is then closed and that's closed, we've got a parallel circuit here. So if we want to work out the current flowing through the heater, we know we use exactly the same formula as we did before. I is equal to V over R, which is 230, but this time we're looking for the resistance of the heater, which is 23 ohms. Okay, so that would be 230 divided by 23, which would be exactly 10 amps. And as that's 10 amps, I'm going to put that in there. That's easy. Then calculate the current flowing out of the battery. Well, the current flowing out of the battery is going to be the total current we're using Kirchhoff's law, remember. So that's going to be the 10 amps plus the 2.5, which gives you 12.5 amps. And then calculate the total power used by the hairdryer. So power is equal to IV. I'm going to use IV. So my total current is 12.5 multiplied by 230, which should give me a power of 2875. Okay, 2875 or 2900 watts. Okay, there's no mark here for the answer for the unit, because the unit is the watt, which you've already been tested on. The next part says the heater is made of a nichrome wire with a length of 1.21 meters. You're given the diameter to calculate the cross-sectional area of the nichrome wire to start off with. The area, well, that's using 1/4 pi d squared. If that's the case, then you're using that's 1/4 times pi times d squared. So d squared, well, d is 0.274, so that's 2.74 times 10 to the power minus 4, all squared. So you square that whole expression there. Okay, and that should come out to be 5.9, well, it's 5.896. Well, okay, well, that's going to round up to 5.90. Okay, times 10 to the minus 8. Okay, so that's 5.90 times 10 to the minus 8 square meters, because you want it in square meters. That's in millimeters, remember. Okay, and then we're on to the next question. The next question says, hence, that means using your previous answer, hence calculate the resistivity of the nichrome wire when the heater is working normally. So the resistivity is, well, resistance is rho L over A, so resistivity is RA over L. Hence, because you're using your value for the area. So the resistance, it said was 23 ohms multiplied by 5.90 times 10 to the minus 8 divided by 1.21 meters, because that's what it tells you the length is in the question, and it's just plugging in the numbers. 1.06 times 10 to the minus 6, and then it's ohm meters. Okay, so you get a mark for the unit, you get 2 marks for the answer with the working. If the only reason why you got that answer wrong was because you'd miscalculated the area, as long as you plugged in your value for the area in here, as long as you substituted in your value, then you get the error accounted for. So you could get all 3 marks even if you got the answer wrong, if it was just because you got the previous question wrong. Then we're looking at the nichrome wire has 1.61 times 10 to the power 27 free electrons per cubic meter. Calculate the mean drift velocity. So we're using what I sometimes call the Mave equation. Okay, so we want to find out what V is. So V is I over NAQ. Okay, so then we're using the current. So we want to find out the current through the heater. So the current through the heater, remember, was 10 amps. And then if we've then got that as your nichrome wire, that would then be 1.61 times 10 to the power 27 electrons per cubic meter multiplied by the area, which you calculated before to be 5.9 times 10 to the minus 8 square meters multiplied by the charge on the electron, which is 1.6 times 10 to the minus 19. So quite a difficult expression, but you just use your calculator to calculate that, and the answer comes out to be 0.6, about 6, something like that. Okay, now, so we've got that one done. In with the UFP questions, there's always one about reading a meter correctly. So you've got a hairdryer here, it's taken apart. It's connected to a very strange looking ohm meter. It's very old fashioned, and you have to calculate the resistance of the actual heating wire itself, and that comes out to be 19 ohms, which you probably notice is lower than the 23 quoted. Okay, now there's a reason for that, because the next part of the question is asking you about the resistance of a heater, of why it's lower than that 23 ohms. Well, the reason being is that there is less current flowing through it because it's just being tested. Okay, and therefore it does not get as hot Okay, so the resistivity is less. Basically, the examiner would look at that and they'd say, well, okay, if that's the case, what have they actually said? Well, the idea that it's not as hot, and the idea about understanding that there is less current, and the idea that the resistivity drops as the temperature is less. Okay, any two out of those would actually get the mark there. So it then says explain why the hairdryer is designed to not to allow the heater to operate without the fan. Well, it's a simple reason: it would overheat. Okay, so the moving air cools the wire. Moving air stops the heater from overheating. Okay, then as you say, as you look through that, you then think, well, what would happen if the fan wasn't there? So without the fan, without the fan, it would overheat. Okay, it's pretty much saying the same thing, but what we're doing is we're qualifying it. We're saying why that fact is relevant. Okay, so the wire could melt is an ideal answer on there. So it would melt or break the circuit. Any two out of those three things will do quite nicely. The only thing is, if you get completely stuck, the obvious thing is if it's overheating, it's a fire hazard. So if you didn't quite get the marks, but you did come some way towards explaining it, but then at the last stage you said it could, you know, it's a fire hazard or it could catch fire, then that would suffice. So that's question number 1. Now on to question number 2 on this walkthrough. So if we start off with the idea that somebody's designed a fridge alarm to sound an alarm if the fridge door is open or if the inside of the fridge gets too warm. It says when the door is left open, the temperature of the thermistor increases and light is incident on the LDR. That means there's light shining on it. State what happens to the resistance of the LDR on the thermistor when this happens. So the resistance of the LDR would decrease, okay, because when you shine light on a light dependent resistor, its resistance decreases, and as the thermistor gets warm, its resistance would also decrease. Remember, it does the opposite to a wire. It says use ideas about charge carriers to explain why the resistance of the thermistor changes in the way described in part A. So the idea is meant to be that using charge carriers, so we're talking about free electrons here. So really we want to be very careful about not sort of coming up with anything too woolly. So the idea is that if you've got a higher temperature, okay, that's the obvious bit, it excites electrons to the conduction band. Okay, if it's then excites the electrons to the conduction band, which then means there are more free electrons, more delocalized electrons, but free is absolutely fine. There are more free electrons and therefore resistance is less. Okay, so the next part for that is really to look at the circuit that's being set up here. So they've got the signal to the alarm circuit comes from here, so we've got basically a potential divider. So it says in the top part of the next part of the question, part C, it says this, the alarm circuit will sound an alarm when the potential difference is equal to or more than 2 volts. So you have to start with the easy bit, which is label the thermistor. So if you look at the circuit diagram, that's your thermistor, label it with a T. And then it says the alarm circuit will sound an alarm when the potential difference across the light dependent resistor and the thermistor is equal to or more than 2 volts. Calculate the combined resistance of the thermistor and LDR required to sound the alarm. In other words, calculate the resistance of this combination for which would give you an output of 2 volts. So this is actually easier than it looks. We're just using a potential divider question here. So we're saying that if we've got the output voltage is V, which is equal to V0 times R over the resistance we're looking for plus 2500. Okay, so if we want to work out the resistance, we just rearrange that and we end up with 2500 divided by, well, it's going to get a bit messy, but I think, well, I might as well do it in one go. Total voltage, which is 4.5, divided by the voltage we want, and then we've got to subtract 1 from that, and we end up with 2000 ohms. Now there's no space for the answer, so we'll always double underline where the answer is so that it makes it clear to the examiner what your actual answer is. It then says, explain why the alarm would be less effective at night. Well, if it's less effective at night, the resistance of the LDR would stay high, simply because there's no light incident on it. We assume there's no actual light inside there's no light being used. Okay, so it will stay high. It's not height, high. Okay, because it's dark. Okay, so then we're shown there to inform the figure in the circuit in circuit in figure 3 is incorrect. What they want us to do is to draw a more appropriate circuit diagram below. So it's actually this actual diagram here. This wouldn't work. The reason being is that we know that when it's light and when it's warm, we know that this resistance will decrease. So the resistance, so the output voltage will decrease, and it says that that should sound alarm when it's more than 2 volts. So we want the resistance to increase. So what we do, the easiest way to do it is to draw exactly the same circuit. So you should use a ruler. I'm not going to, because I'm trying to do this quite quickly, otherwise I will bore you silly. So you've got your thermistor, you've got your LDR, and you've got your sort of 2500 volt, 2500 ohm resistor there. So you would want it to feed off from that one there, like that. Okay, and that's that question done. So the idea is meant to be that as we've got a 4.5 volt battery here, as it gets light and warm, this resistance would decrease, which means that the PD across here is less, so the PD across here is going to be more. That's what we want. So on to the next part, which is question number 3. You got an internal resistance question. Okay, now this is the classic graph question, so you need to first of all define internal resistance. Well, internal resistance is a resistance causing a loss of potential difference when a current passes through the cell. Or we could say it's drawn from the cell. There are lots of different definitions of internal resistance. As long as you write the correct one, as long as you write a correct definition, you're absolutely fine. And the EMF is the energy supplied per coulomb of charge, or per unit charge. You could also think of it, I'm going to hedge my bets a little bit, it's also the PD when there is no load current. Okay, because when there's no current being drawn from the battery, the terminal PD is equal to the EMF of the cell. So the next one, we've got going to calculate some averages, and we've got to do this correctly. So the average each time, we just add them together, press equals on the calculator and divide by 2. and we should be expressing it to 2 decimal places as per our values, and if that involves rounding off, so be it. Okay, so that's your values, and again this is obviously the question hasn't come up yet, but you can tell straight away if you've got blank mean values in here, you can bet your bottom dollar you're going to get asked to do that. And lo and behold, part 1 of the question tells you to calculate the mean values of potential difference, quoting values from an appropriate number of significant figures. Okay, so that is your appropriate mean there. So what we're then doing is we're drawing a graph. Now if you're drawing a graph, you've got to remember your basic rules, and this is why your teacher has gives you such a hard time over your graphs. So we start off with our basic graph here. We've got we know that for the current we're going to start off at 0, okay, because the current goes down quite significantly from a maximum value to a value close to 0. The mean starts at about the mean terminal PD starts at 0.6, goes up to 1.3, so it wouldn't be appropriate to start that one from 0. So if we go up in 0.1 amps, like that. I'm using pen here so that you can see what I'm writing, but in actual fact we probably would use a pencil in real life. It's just that on the camera I've found that using a pencil doesn't show up very well, and you can't see what you're doing. You can't see what I'm doing. So there's your x-axis. It has to be labelled, so we label it current I in amps. Okay, name, symbol, unit, name, current, symbol I, unit, amps. And the same goes for voltage. We're going to start at 0.6 because we don't go any lower than that, and we're going to go up to about 1.6. so the best way to do that is to go up in 0.2s. Okay, and we're going to call that terminal PD. Oops, don't go off the top. It's V and it's in volts. Okay, so that's name, symbol, volt, V, unit, volts. So if we then just plot the results correctly, well, it starts at 0.2 where it's 1.3, so that's exactly there. Then you've got 0.35, which is there. It's at 1.16, so 1.1 is there. 1.1246 goes there. Next one is 0.5 amps. At 0.5, that would be at 0.96, so 0.9 is there. 9246 goes there. Then we've got 0.65 amps. It's 0.86, so there's your 5 there. 0.8, and against 8.6, so it's 246. And at 0.8, it's actually exactly 0.6, so you put the cross in there as clearly as you possibly can. We're then constructing a line of best fit. The basic rule about lines of best fit are that you should follow the trend, and it should have roughly the same number of points above and below the line if possible. So I'm just going to just construct my line of best fit as best as I possibly can, as carefully as I possibly can. Probably about, I reckon, about there. Again, in an exam you are given quite a bit of leeway in terms of your lines of best fit. As long as you followed the basic rules, it's absolutely fine if it's slightly off. It just takes a little bit of figuring out. See, that would be inappropriate because you've got 2 lines below and none above. That one would be just about okay because you've got 1 below, 1 above, and the other 2 are pretty much on the line, so that will probably do it. Okay, so we've got that one, and then you've got a space for gradient and intercept. Well, that's part 3, isn't it? Measure the gradient and intercept of the graph. So if you want to get the intercept first of all, that's easy. That's there, so that's 1.5 there, 5.2, 5.4, 5.6, 5.8. So intercept is 1.58. Now, I know that's going to be the EMF, so I'm going to say V for volts. And as long as you're sort of within a certain sort of boundary there, you're absolutely fine. Okay. Now to measure the gradient, remember the basic rules. We want a big triangle. Big is beautiful. We choose a couple of convenient points. One at the top of the line up here, where it's easy to read, and we look for another one at the bottom of the line where it's easy to read. Well, there's a nice one just there. So I'm going to draw my triangle. We always draw the triangle so that the examiner can verify that you have correctly measured your gradient, because remember, you are awarded marks on correct technique, not necessarily the answer, which is why the triangle is important. In fact, if you don't draw the triangle, you run a very real risk of not getting any marks at all if the examiner can't tell what you did. So we're just going to follow this through, and we've got Y2, Y1, X1, X2. Well, Y2 is 1.4246. That's 1.46 volts. Y1 is exactly 0.8. X2 is 0.1. And X1 is 0.6. 1, 2, 3, 4. 0.64. So I'm putting that on the graph there so you can actually see that that's what I've read there. So then I say that the gradient is Y1 minus Y2 over X1 minus X2. Now if that's the case, then what we want to be doing here is saying Y1 minus Y2 over X1 minus X2. So we just substitute in our values. So Y1 is 0.8. Y2 is 1.46 divided by X1, which is 0.64, minus 0.1, which would be, just get your calculator out and work it out. So you'd say, well, that's going to be 0.8 minus 1.46 equals, divide it by 0.64 minus 0.1, and then we press equals, and we end up with 1.2 recurring. So I'm just going to write that there. So the gradient, well, it's going to be about 1.22, and here's where we've got to think carefully. It's minus 1.2, of course, so it's minus 1.22. And those of you in the know, of course, would know that that's actually going to give you internal resistance, but I'm going to put ohms in there just to be clever, because I reckon it's probably going to come up. Okay. Right, on to the next part of the question, which is you have to then state your values for internal resistance and the EMF of the cell. Well, the EMF was exactly the same as it's the intercept, so that was 1.58 volts. And the internal resistance is 1.22 ohms. Then it says after a lot of use the experiment becomes run down. In the experiment the cell becomes run down. So it says state what effect this has on the internal resistance of the cell. Well, so this would increase it. So just to say it increases. You don't have to write full sentences or anything clever, just wants a statement. Then this is a bit harder. Explain why you cannot find out if the cell is becoming run down simply by connecting it to a high impedance voltmeter, because the voltmeter the voltmeter will not draw any current. Draws little or no current. Okay, and therefore it would read the EMF of the cell, give you a more closer indication of the EMF of the cell, which does not change much. Does not decrease actually until the cell is nearly flat. Okay. The next part, the last part of the question, evaluate the use of low internal resistance batteries for portable devices such as mobile phones. So evaluate's talking about their pros and cons. Okay, so if it's low internal resistance, you can get high currents. Okay, if it's low internal resistance, high currents, and therefore higher power available. However, they can overheat the circuit if there is a fault. Okay, and that is the end of that question. That's the basic idea. So we're now on to question number 4, which is the one about semiconductors. Now, this is one of the last topics, so you may not have come across this one yet. But semiconductors are basically halfway between conductors and insulators, in that the top conduction band with a conductor is kind of mixed in with the valence band, so the valence electrons can join the conduction band with no need for any extra energy, and so can actually conduct electricity. With a semiconductor, the valence band of electrons is below the conduction band, okay, with a little bit of a gap, and it changes the way it behaves electronically. Anyway, the question says, describe the arrangement of charge carriers in an N-type semiconductor. You may use the diagram as part of your description. Well, basically what happens with an N-type, N is for negative. To make something negative, you need to add electrons. So in a semiconductor, the electrons are stuck in the valence band. Okay? So these are, that circle is an electron. Okay? And what happens is in an N-type, you'll have a few extra electrons, which, because the valence band is full, have to be in the conduction band, which means that they're free electrons or delocalized, and they can flow. So these are extra electrons. So you add another material, and suddenly you can't fit all the electrons in the valence band, so some are in the conduction band of the material, and therefore it's N-type, and it allows current to flow. Okay, so it's basically, the key idea is the valence band is full, the conduction band has the extra electrons, allowing current to flow. Okay, so that's the idea. A semiconductor's usually like a conductor, or almost like an insulator, but if you dope it, its resistance decreases because you've got extra electrons in the conduction band if it's N-type. So N-type, remember, N means negative, electrons are negative, so you've got extra electrons. Describe how electrons, how semiconductors are arranged in a diode, and explain why diodes only allow current to flow one way. You may use a diagram. Now, just a little point, both these questions said you may use a diagram as part of your answer. When you see a question that says that, take the hint, draw a diagram, label it. So, because the diagram is often enough to get the mark sometimes if you've labelled it correctly. So the whole point about diodes is you have two types of semiconductor. So if I draw a diode in what we call reverse bias, it's basically like a sandwich, and if you take an N-type and a P-type and you connect it, well, some people refer to it as the wrong way round. It's not really the right way to speak about it, but it'll do. If you refer to connect it on reverse bias, positive and negative, basically what happens is that the electrons from the N-type go into the holes created by the P-type, so you end up with an area here with just neutral which acts like a neutral semiconductor, and doesn't allow any charges to sort of flow, so no current can flow, and we call that a depletion zone. So what's happened here is all the excess electrons from the n-type have basically filled in the holes created by having too few electrons in the p-type semiconductor, and you've ended up with just ordinary semiconductor, which is insulating, and therefore there's no charge carriers. It's depleted of charge carriers, so we call it a depletion zone. Okay. If you take it on a forward bias, we know that when we connect we connect these things up, connect diodes up the right way round, as they sometimes say, what you end up with is no depletion zone. So you've got charge carriers on both the N and P side of a diode. So what you end up with is negative, get it right, and a positive there. We know that we have no depletion zone. No depletion zone. My handwriting's not very good because I'm getting tired now, but never mind. You could also describe it. Well, okay, if we've got a reverse bias, we better call it that up here. And if that's reverse, then that's going to be forward, isn't it? A bit like the gears on an automatic car. Forward bias, reverse bias. Okay. Well, you're going to have a larger depletion zone, which means you've got a high resistance, and a forward bias you end up with no depletion zone, and that means you've got a low resistance. Okay, in other words, it allows current to flow. It's not really enough to say that, so I want to be really firm about this. So I think it's worth actually putting in the depletion zone in here and in here and here and here, and just putting a little star to just to explain depletion zone has no charge carriers. Okay, right, so then we've got another one. Now we've got another graphy question, but this time the graph is drawn for us because you've already been assessed on your ability to draw graphs. So we've got here question 5. Figure 5 shows a circuit diagram of a circuit used to investigate the change in potential difference of a capacitor. So we've got 5 volts, we've got the capacitor, we've got a voltmeter, we've got a resistor, and we've got a switch. So if we think about it, if we want to close that switch, calculate the current flowing through the resistor when the switch is closed. It doesn't matter what we've got here. This is in parallel, so this has no effect on this. So as soon as we close that switch, we know that the current is the voltage divided by resistance. So the voltage is 5, the resistance is 20 kilo ohms, so it's 20 times 10 to the power of 3. And then as we've got that, we then just calculate it very quickly. It's 2.5 times 10 to the power of minus 4 amps. Okay, no space for writing the answer, so we double underline the answer to make sure that we can show the examiner where it is. And then you've got your capacitor discharge curve. This ought to be very familiar to you by now. So as you've got this capacitor discharge curve, what you need to do is look at the next part of the circuit. So the next part of the circuit, next part of the question, I should say, says find the time constant for the circuit. So the time constant, remember, is when it falls to 37% of the original value. It's also equal to CR, but of course, if you look at the question, you're not given the capacitance here, okay? You're also asked to calculate the capacitance, so obviously you've got to find it from the graph. So we know is when V is 37% of the original voltage, okay? That's a definition of time constant. So we're just looking for 37% of 5. Okay, comes out to be 2 point. Sorry, let's calculate it. My mental arithmetic's not what it used to be. 0.37 times 5 gives me 1.85 volts. Okay, and then when I've got that, I then go back to my graph and I look for where 1.85 is. So there's 1.2, 4, 6, 8, 8.5 is about there. So I just take my ruler, because we always use a ruler for straight lines, don't we? And I just draw my line straight across there. It doesn't matter if you're slightly out. It's not that big a deal as long as you're showing the correct technique. I mean, obviously, if you're way out, then you're not using the correct technique. But if it's very easy to, if you're a tiny bit out, as long as you're using the correct technique, that's usually good enough. So here we've got to work out what this is. Well, we've got 5 divisions between 20, so each one of those is going to be 4. So it's 44 seconds. And we just double check that we've got that scale right. We'll do 40, 44, 48, 52, 56, 60. Yeah, that is correct. So that's 44 seconds there is the time constant. So if I take that, that would be then 44 seconds read from the graph. Okay, now the examiner, when they're marking this, they'll be looking for, did you work out what 37% of 5 volts was, or 0.37 times 5? Did you read it off the graph? If you got either one of those bits wrong but you did the other bit right, then they would actually give you 1 out of the 2 marks. So this is where working is really important. There says hence, which means using the previous question, using the previous answer, calculate the capacitance of the capacitor. Well, we know the time constant is capacitance times resistance. So if that's the case, we want to calculate the capacitance. Well, the capacitance is going to be the time constant divided by resistance, which is going to be 44 divided by, well, resistance was 20 kilo ohms, so that's 2 times 10 to the power 4 ohms. You could say 20 times 10 to the power 3 as I did before, but it comes out the same. And it comes out to be 2.2 times 10 to the minus 4 farads. Now it doesn't ask for it in microfarads. You could be clever and work it out that it's 220 microfarads, but that's more trouble than it's worth, because if you get that bit wrong, you might lose the mark. Whereas if you've actually done the question right, it's fine. You get the mark. So you just, so try not to be too clever about that. It then says, show the time taken for the voltage across a capacitor for the half of its original value is given by that. One word, yuck. This is not an easy question. This is one of these high-level questions. This is really for distinction-only candidates, because you have to be very good at maths to do this. But it's relatively simple if you know how. You know the voltage is equal to V0 times e to the power of minus t over CR. And if it's full to half of its original value, V is equal to V0 over 2. So the two things, so we can substitute that in. V0 over 2 equals V0 times e to the minus t over CR. The V0s cancel, so we end up with a half equals e to the minus t over CR. So we've got the natural log of a half. Well, the natural log of e to the power of anything is just what it is, so it's minus t over CR. Okay. I've used a lowercase t, I've just realised, but never mind, it doesn't matter. So log to the power of a half is the same thing as saying negative ln2, negative log of 2. Okay, is equal to minus t over CR. We can get rid of that pesky negative sign, and then that implies that t is equal to CR times the natural log of 2, which is therefore shown. Now this is worth 2 marks, and they're 2 very hard fought marks. So what are they really after? The examiner is really after the idea that is saying that it's the time taken of the voltage to fall to V0 over 2. So even if you really don't get this exponential and log stuff, if you just do the obvious bit, you got half the marks. You've only lost 1 mark, But if you are good at working with logs, obviously you work through, you show your steps. The idea is meant to be that if you show the correct technique, you get the marks. Okay, it's as simple as that. So we're now on to the last part. Now this is one that you might do in class sometimes. You've got a thunderstorm with a cloud covering an area of 2 square kilometers, discharges completely to the ground, which is 2 kilometers below it, when the voltage between the cloud and the ground reaches 100 million volts. This is called a lightning strike. Okay, you might be thinking, what on earth is this? Well, it's a capacitor. If you think about it, in a thunderstorm, you've got your cloud. Well, let's just assume for the sake of argument it's positively charged, and you've got your ground. Your ground conducts and therefore induces a slight negative charge to it. Okay, so you've got your distance and you've got your surface area. Okay, so to calculate the capacitance, we're looking at calculating the capacitance from mechanical measurements. So that would be capacitance is epsilon naught A over D. So epsilon naught is, again, it's on your formula sheet, it's 8.85 times 10 to the minus 12 multiplied by the area, which it says is 2 square kilometers. Now careful, a square kilometer is 1,000 by 1,000, okay, which means it's 10 to the power of 6, and that's 1 kilometer squared. So it's 1 kilometer squared is 10 to the power of 6 square meters. Loads of people forget that. Don't worry if you do. It's only 1 mark that gets dropped if you make that mistake. But we want to get it right if we can. It's 2 of them. So it's 2 times 10 to the power of 6 square meters divided by D, which is 2 kilometers. Well, that's going to be 2 times 10 to the power of 3 meters, obviously. And there's a straight calculation. You plug it into your calculator, and for some strange reason, probably because I planned it that way when I wrote the question, it comes out to be a nice convenient number. Okay, and it is a tiny capacitance. Okay, it's a surprisingly small capacitance. A lot of people think that because thunderclouds store a lot of, there seems to be a lot of charge and energy being discharged by it, it's obviously a very big capacitance. It's not, it's tiny. It's just a very high voltage. So we then calculate the charge in the cloud before it discharges. So the charge Q equals CV. Okay, so the capacitance is 8.85 times 10 to the power minus 9 multiplied by the voltage, which is 100 megavolts. Remember, mega means million, and so we say 100 times 10 to the power of 6. Okay, and then that gives you the charge stored, which doesn't sound like a lot, but it comes out to be 0.885 coulombs. Okay, there's no space for the answer, so you just want to double underline the answer you got, so it's clear that that's what your final answer is. Okay, it's 1 mark. 1 mark for showing that working, 1 mark for then using that answer. Don't forget that even if you couldn't do this, the previous part of the question, you should give some kind of guess as to what the answer might be, because you can use it here and still get the 2 marks because the error carries forward. So if you can't, if you've got a structured question like this, and you really can't do the bit before it, just make something up and use it for the next question. You'll still get the marks on that next question. Then for part 3, it says calculate the energy transfer during the lightning strike. So the energy, well, there's lots of different formulae. I'm going to use, just because it's different from the one I demonstrate, it's a half CV squared, which so it's a half times the capacitance, which is 8.85 times 10 to the minus 9 multiplied by the voltage squared. So that's well, 100 times 10 to the power of 6 is 10 to the power of 8, 10 to the power of 8 squared. Okay, and you end up with 4.45 times 10 to the power of 7 joules of energy. And it's that easy. Okay, and there it is. Okay, it's a lot of energy. Remember, think of Back to the Future, and it's lots of gigawatts of energy, of power being used to power Marty McFly's time machine. But either way, there you go. There's your there's your energy. So that's the last main question. Now we're on to the multiple guess questions. Sorry, did I say multiple guess? I meant multiple choice. Now, if I've got my multiple choice questions here, there are two types of multiple choice questions. There are hard ones and easy ones. I know that sounds obvious, but actually it's important, because sometimes you can go through, if you're really having a struggle, you get to the end of the question, at the end of the paper, and you're really starting to get tired. Just go through the easy multiple choice questions. If you need a brain break halfway through, go to the multiple choice section and just do the easy ones, so that you've got a clear, so that you've got a few points quite easily and given yourself a bit of a break. So what's the name given to the process of adding an impurity to a semiconductor? That is called doping. There's actually a clue in the question earlier on in the paper. What is the charge carrier density of a material? It's the number of free electrons per unit volume. These are definitions. While we're here, I can't stress how important it is. I can't stress enough how important it is that you learn your definitions. It's very important. So what is the correct formula for the energy dissipated by a resistor? Well, there are lots of different ones. You've just basically got to go through. Well, current divided by PD. Well, that's not really anything. Well, it's not really anything. It's 1 over the resistance. Current times resistance times time. Well, that's voltage times time basically. So that's nonsense. PD times resistance times time. That's just nonsense. So it's current squared times resistance times time. If you think about it, P equals I squared R. So power times time, which is work done, it's IRT. It's that one. So what is the name for a component for which the PD is proportional to the current flowing through it? That's again a definition of an ohmic device. Okay. And number 10, diodes become conducting when, now you've got to get this right, it's when they're connected in forward bias, because reverse bias, you know straight away it won't conduct unless you have a massive voltage which exceeds the breakdown voltage, and the PD's got to exceed the trigger PD. Okay, you come across that in questions before now, I should hope. Next one is what are the charge carriers in a liquid? Remember, in a liquid, in a solid we know it's free electrons, but in a liquid, so you may remember from your old chemistry lessons that they are ions. The next question says, what's the definition of potential difference? Now you've got to remember it's the volts, it's the number, it's the energy per unit charge, isn't it? Okay, 1 volt is 1 joule per coulomb. In which situation would the PD across the resistor not be 5.0 volts? So when it's connected to 5 volts with negligible internal resistance, no, the PD would be 5 volts if it's got no internal resistance. When it's connected to a cell of EMF of 10 volts and the internal resistance is equal to the resistance of the resistor, well, if that's going to be the same, the EMF would be half, so that would mean the PD would be half the EMF, so that would still be 5 volts. So this is quite a hard one. So when it's connected to a cell of EMF of 10 volts with negligible internal resistance, well, the terminal PD then would be 10 volts, so it's not 5. And this one again is EMF is equal to 15 volts with internal resistance equal to twice the resistance of the resistor. This is not an easy question to even decode, but it's, again, as I said, 20% of the paper is meant to be distinction level work. So 14, when measuring the resistivity of a wire, why should the current in the wire be kept constant? It's because, if you remember, the resistance of a wire will increase with temperature. So we want to try and keep the temperature of the wire constant by keeping the current constant, or as constant as we can reasonably do. Typical internal resistance of an alkaline battery. Well, you did the internal resistance experiment. You know that internal resistance is typically round about an ohm or 2 ohms at the most. So 0.5 ohms would be a sensible typical value. And that is the 2018 December past paper for you. What you'll be required to do in the next lesson is to have a go at the whole paper yourself, having watched this video a couple of times and made some notes, so that you know how to answer the questions. So enjoy watching again, and my advice is that when you're watching a second time, if there's a bit of the question you don't know how I did it, what I'd suggest is you hit pause and go back to your book, look up that particular chapter, and I'm sure you'll find some useful information in there.